As I already mentioned several times, about 20 years ago, we saw a shift from voice only more and more towards voice plus data transmission, more and more data transmission. So how is this reflected in the GSM system? As you know, the original data rate is only something like 9.6 kilobit per second, maybe using a different coding, so less redundancy, something like 14.4 kilobit per second. This was okay for transmitting a fax, but this is really not enough for internet, surfing the web or multimedia. So the first step towards higher data rates was combining several of the time slots. So this was mainly a software update. So basically, you bundle time slots. For example, if we look here on the full rate traffic channel offering 9.6 kilobit per second, by using 2 time slots, we already have 19.2. By using 4 time slots, 38.4 kilobit per second. If we then go to a different coding, less redundancy, that means we can achieve almost 60 kilobit per second. So that's the so-called air interface user rate, 57.6 kilobit per second, by using 4 time slots at 14.4 kilobit per second. So the big advantage of this technology, which is called high-speed circuit switch data, so high speed at that time relative to 9.6 kilobit per second, the big advantage was it was basically ready to use, it was a software update, and you had a constant quality. It was relatively simple because you don't have to change anything with the slots. You do not need new components. The big disadvantage was, well, you block channels for voice transmission. Imagine a file download or a web page download. This is a rather bursty traffic. And if you use circuit switching, that means you block a circuit if you need it or not. However, you have a constant quality. So using this HSCSD guarantees you certain quality of service, a certain data rate, as long as there are enough free slots in a time frame. Imagine you have to hand over from one cell to another. In the next cell, you do not only need a single slot, but several slots. This technology was not offered by all network operators because, yes, there were some usage scenarios like video conferencing, maybe, but the typical use for data transmission was rather bursty traffic, surfing the web, downloading email. So this meant, many years ago, the introduction of a new transmission paradigm, new technology. So the next step was the introduction of packet switching. So that's something completely new for the complete circuit switched GSM network. So GPRS, the General Packet Radio Service, that was the new technology. So packet switching. Packet switching, well known from, for example, the internet, but not used in the classical telephone networks. So the idea there is use empty slots only if you have any data ready to send. So you can use several slots in a time frame, achieving, for example, something like 50 kilobit per second. So the introduction was in the year 2001. And this was not only kind of a paradigm shift going from circuit switching to packet switching, but this was also one step towards UMTS. As we will see when I discuss third generation, GPRS introduced the new packet switch part needed for the UMTS architecture. It's a more flexible technology because you can use resources, time slots on demand, but it's also more expensive because you need new hardware, basically routers. As we will see when we discuss the architecture, there are some new network elements so-called GPRS support nodes. There are gateways, the gateway GPRS support nodes, and serving GPRS support nodes. So basically routers. So you need some interworking units between any packet data networks. Think of the internet and the new GPRS network. And you need some more of these devices supporting the mobile station for, well, managing the location, billing, some security issues. And then we have a register, a GPRS register, that stores the user addresses, the IP addresses of mobile phones. I will come back to the architecture in a minute. So, what do we achieve and what was the idea? GPRS was never meant to be a high-performance, real-time packet switching service. Everyone knew this is now put on top of a mobile network, a cellular network. So you cannot have these high-quality guarantees you expect from a fiber optic fixed network. The idea of GPRS when it comes to quality of service was offering packet switching, but, well, with always keeping the mobile network in mind. So if you look, for example, at the loss probabilities, so the lost service data unit probability or duplicate service data unit probability or out of sequence probability, corrupt SDU probabilities, then you will see, depending on a so-called reliability class, this is not something like 10 to the minus 10, 12, 15, whatever, like you might have in fixed networks, but these are probabilities magnitudes of order lower. So 10 to the minus whatever 5 duplicate probabilities. So it can happen that you lose SDUs, that you have out of sequence SDUs, corrupted SDUs. And you have to correct this on higher layers. So that's a different, for example, to circuit switching. Why do we have these higher probabilities for loss or duplicated SDUs? Because we cannot really guarantee transmission. We have the effects of handover. So we might lose a packet, for example. So we might retransmit packets via different antennas so we can duplicate them, etc. Especially when you look at the delay classes, you see, oh, that's completely different from what I expect from fixed networks. Think of, for example, you want to transmit a kilobyte. So the mean values for transmitting a kilobyte for the delay are for the best delay class something like 2 seconds. And for the worst delay class, it's unspecified. And 95% of the packets, of 1 kilobyte packets, will reach you within 7 seconds. So we are talking about seconds. In fixed networks, we are talking about milliseconds. So across a country, you have delays of whatever, 10 milliseconds, something like this. Here we are talking about seconds. Why? Well, first of all, it takes some time from the mobile station to the base transceiver station because of the algorithmic complexity, forward error correction. I explained this already. And then, in addition, GPRS cannot immediately access the medium, but first it has to use a packet random access channel. And there you use this kind of slotted ALOA scheme. You might have collisions and you compete for empty slots. And what happens if you have a really busy area with many people using the mobile phone for voice calls? Well, the system tries to squeeze in from time to time a packet for GPRS. So usually you will have at least a time slot for GPRS and then the other time slots for voice calls because you can generate more money out of voice calls. So this will leave at least a single slot for all the GPRS users. So you will not have this kind of starvation, for example, of TCP connections, but data rate will be very low. So you will not have round-trip times of, let's say, 100 milliseconds or 200 milliseconds, but rather round-trip times in the order of many seconds. This has a lot of implications when you think of congestion control in TCP and all these control loops. So the problem is this takes time. Think of accessing a web page via GPRS, setting all these round-trip time parameters in the higher layer protocols. I will come back to this when I discuss TCP. So here you see, you will not have hard guarantees even for the best delay class. You will only have the 95 percentile. So 95% of the packets will reach you in less than 7 seconds, but there will be 5% with whatever delay. So we don't know. So in the very early days of GPRS, the first experiments showed that sometimes packets needed half an hour, something like this, due to congestion, due to whatever problems, to reach the destination. So GPRS was never meant as a system for real-time interactive robot control or gaming, whatever. Although you might have data rates of, let's say, 50 kilobit per second, you cannot have any real-time control using GPRS. So this GPRS is rather meant for emails or download of web pages, download of messages, background downloading of something, but not interactive messaging, for example. This really doesn't work because it takes some time, depending on the load in a cell. Okay, so keep this in mind, not a real-time interactive system. Now the first devices using GPRS, well, you can classify them using GPRS device classes. And typical devices were, for example, classes 10 or 12. What does it mean? You can have per TDMA frame up to 4 receiving slots and 2 sending slots. So looking at a typical frame, you could have, for example, receiving, 4 slots. Then you switch your transceiver from receiving into sending mode, and then you can send, and then you switch back from sending mode into receiving mode again. So the transceiver needs a certain time for switching back and forth between the receiving and the sending slots, and then in addition you might have a maximum number of slots you're allowed to use. There are several reasons for this. So in the early days you do not want to overheat your transceivers, because usually the original transceivers were built for using a single slot in a TDMA frame, and now you use them for example, 5 slots or whatever. So there are some more technical engineering reasons for not using all the slots. Plus, in addition, theoretically, you can go up to 8 receiving slots and 8 sending slots, using them all 8 slots. So using them at the same time, then the problem occurs sending and receiving at the same time. So it's very, I would say, expensive to build transceivers for this, using sending and receiving at the same time, because although you use frequency division duplex, the frequencies are pretty close, and the sending power of your power amplifier is much stronger than really the weak power the signal has when it reaches you. So that was the basic idea for the GPRS device class. So what are the data rates you can achieve in the end? So the user data rates depend on the number of slots you're using, single slot or up to 8 slots, and it depends on the so-called coding scheme. The coding scheme basically tells you how much redundancy you will have, how you code your bits. The typical coding schemes supported by network operators are coding scheme 1 and 2. So this depends on the network operator. And then a very typical GPRS device can, for example, receive up to 53.6 kilobit per second using 4 slots per TDMA time frame. using the coding scheme 2. So you can look this up in literature. What does it mean? Coding scheme 1, 2, 3, 4. So these are quite typical GPRS user data rates. So what does GPRS mean when it comes to the architecture? Well, GPRS, as I already told you, introduces new elements. The new elements are mainly routers. The GPRS support nodes. So you might have the internet somewhere, and then you have a gateway, GPRS support node. You have defined interfaces, as always in these architectures. And then you have several of the serving GPRS support nodes, so routers. So that in the end, you have basically a similar architecture like the internet. And now we can forward the packets from the router to the BSS. You know the BSS, the base receiver stations and the base station controllers, then forward the data to the mobile station. So these are the additional elements, and you will have a register because it's important for the system to know the IP address. It's quite common to use so-called private IP addresses for the mobile station. So the mobile station is something like 10. Whatever. So private classical IP version 4, version 6 IP address, so private addresses. Sometimes some of the operators also offer global IP addresses. The problem is that if the device is really visible to the outside world can also attack the device. So although private IP addresses are not really good security mechanisms, at least they enable a certain kind of separation of the private network and the public network. And if you use private addresses, then you have to do a network address translation here so that you can use services from the internet. So, but that's the classical way you also do on any other fixed network. So you see that GPRS introduces new elements in addition to the already existing elements of the GSM network. GPRS also introduces new protocols. So those were the old days when not internet-only protocols dominated the communication world. So we have some special protocols still there. So this is the classical MAC and radio layer, radio link control, so layer 2 protocols, and then up to layer 3 here for routing. And you see that now, and that's new, we can use IP across many other protocols special for mobile networks and frame relay and whatever technology. But here we can use IP as we are used to do in the internet. So now we can transmit IP packets from wherever in the world using the routers inside the GPRS network, forwarding the packets to the mobile station. So this is where your layer 3 from the internet starts. Underneath this layer, we have several more protocols, and you see this increases the complexity, a lot of encapsulation. So we use tunneling protocols, and we can use UDP, TCP, and IP again, because we need a layer 3 protocol inside the network. As you see, your user data is encapsulated in several other protocols, but from the end system perspective, this is kind of transparent. Okay, we have a maximum packet size and all these problems, but this is kind of transparent transmission from the mobile station into the network and vice versa. And underneath all these layers, underneath layer 3, we have all the others. Logical link control and all the other layer 1, layer 2 protocols we use inside the network. So you as a user will not see all this. So new elements and new possibilities. So that is basically all about GSM and the classical second generation system. So now, several questions. Go back into the GSM architecture and check what kind of multiplexing is used on different layers of the hierarchy. For what purpose? So we do not only have the physical layers, we have several more layers. How do we synchronize the mobile station with the base transceiver station? Who is responsible for synchronization? Why is this synchronization extremely important? We saw roughly 20 years ago the shift from voice only more and more towards kind of internet style traffic. Well, it's not like the internet, but still it's internet style traffic. How's this reflected? Why do we need new infrastructure for GPRS, not for HSCSD? Which components are new and what's their purpose? Well, looking back, only few operators really offered HSCSD. Why? What was the problem? Now looking at the performance of the GPRS systems, why do we have these extreme high delays for the packet data? Why not in circuit data? What is the difference? So what would you pick for which kind of application? So looking at GPRS from today's perspective, well, relatively high delay, low reliability, why was this still a breakthrough in the GSM world? Now think of a GSM cell. What are the limitations in terms of diameter, capacity, voice and data for traditional GSM, for HSCSD, for GPRS? How can you increase the capacity? There are different ways of doing this. I talked about coding schemes. Look it up and now answer what determines the coding scheme. Why do we have to switch from one coding scheme to another? Now focusing on handover. Give some reasons for handover and the problems associated with the handover. Which are the typical steps for handover? What types of handover can occur? And then think of the resources we need during the handover for data transmission using the new schemes HSCSD or GPRS. What happens with certain quality of service guarantees when we perform the handover?